Hey everybody, it's Mr. N here, and we are going to talk about the derivative today, along with rates of change, which is 3-1 in the 6th edition, but 2-7 in the 9th edition. So, let's go back to that process when we had to find a tangent line, and what we did was, suppose we had some curve here, and I had a point P and a point Q, and I said that we needed to bring point Q as close to point P as possible. So this process of finding that tangent line is really called the derivative. So we're taking point Q and we're bringing it as close to P as possible. So do you remember what we did there? We said that this is at A comma f of A. So let me write that down. This is at A comma f of A, and this right here would be at x comma f of x. And then we said that we needed to find the slope, so we said f of x minus f of a over x minus a, and we had to find this slope from P to Q, and we are going to take Q and put it as close to P as possible, so we're finding the limit. So we're finding the limit as x goes to A of the slope from P to Q. We found the slope, then we plugged in the point, and we got y equals mx plus b, or as we had said, just keep it as y minus y1 equals m times x minus x1. Okay, and we plugged it in and we solved. So everybody was okay with that. And that was the tangent line that we got. And we ended up as defining the tangent line as to the curve at y equals f of x at point P, A of A, as a line through P such that the slope from is the limit as x approaches A of f of x minus f of A over x minus A, which is what we just did above. So now here's what I'm going to do. Okay, so we know this. This is what we said above, the limit as x approaches A. I want to call this distance, let me slide this up a little bit so we can get a better look at it, and I'm going to zoom in. So let me zoom in on it like this, and I want to call this distance from here to here, I'm going to call that h. Right? We know that this distance right here, we know that this is A, this is x, right? So we're going to call that distance h. So h will be the distance of x minus a. If I were to take this and solve for x, I would get x equals the a plus h, or you could say h plus a. It doesn't matter, either way. But we're going to probably most likely use this one for a little bit right now. So this distance I called h right in here, okay? And I put this above for you guys so you could see x is the a plus h, or h plus a. So then as x, and let's scroll this down so we can see the rest of it. So that tells me that as x goes to this a value, h will go to 0. Do you understand what I'm saying by that? Since h is x minus a, as x gets closer to a, these two will be the same value. H will go to 0. Right? So as x gets closer to a, look at it here visually, as x gets closer to a, h, that distance becomes 0. So basically what I'm trying to do is I'm trying to get, since I want the limit, I'm going to try to get the limit as that h goes to 0. So now let me plug in some other things. This f of x, this would be f of a plus h, right? So since I called that distance right here x, instead I used the h, I end up with f of x right here. This would be the same as plugging it in. This would be f of a plus h. So all I'm doing is doing a little bit of manipulation with some variables and introducing this h. So the slope from P to Q is equal to f of a plus h minus f of a. So it's the same thing. Now, instead of x minus a, I put in the h. All I did was adjust this a little bit. So now, instead of taking the limit as x goes to a, I want to take the limit as h goes to 0. And this is what I end up with. That's the derivative of a function at point A. It's the same thing as we did taking the slope from P to Q, but instead I have replaced this. Oops, this is a mistake here. Oops. And a big typo in the notes. This should say h right there. So let's fix that, make sure, because now we're taking h as it goes to 0. So the slope is the limit as h goes to 0 of f of a plus h minus f of a all over h, and that equals the derivative, and we are going to call the derivative f prime of a. This, when I say the word prime, tells me that it's a derivative. Okay, so I will use this symbol f prime of a. So that is the tangent line. And then for velocity, since we've done these velocity problems, it's very similar. So the velocity at a is the limit as h goes to 0 of f of a plus h minus f of a over h. So we're taking this time as h goes to 0. It's the same exact process as we did above. I just showed you how we got this a plus h and this h instead. We just introduced this new variable h. That way we could take it as h goes to 0. It just makes things a little bit easier as we take it as it goes to 0. So for instantaneous velocity, that is the velocity at a point, and so this is how we're going to get instantaneous velocity. The instantaneous velocity is that tangent slope that we talked about prior. So everything has stayed the same. We've just introduced a new variable, h, and now we're taking the limit as h goes to 0, just as we did before with p getting close to, or q getting close to p. Okay, and that is what we're going to define as a derivative. So with respect to rate of change, let's talk about all of this. Now, the rate of change is delta x, which is x2 minus x1. So right here, x2 minus x1, that's delta x. If I call this point right here x1, f of x1, and that point right there, x2, f of x2. So that means our delta y would be right up here, which is f of x2 minus f of x1. So the slope is the change in y over the change of x. You've learned this basic concept many, many, many years ago of the slope. So delta y over delta x, change in y over change of x, is the slope. Delta y, we said, is f of x2 minus f of x1. So if I find just the slope from P to Q, so if no matter how I do this, and I find from P to whatever Q is and however it's connected in between, this is a secant line, okay? That's a secant. And that's going to give me an average rate of change. How do I get an instantaneous rate of change? Well, I need to find the point that I'm getting to. If I'm going to point P, remember we're making Q as close to P as possible, which will give me a tangent line. This is a tangent. So a secant is the average. A tangent is the instantaneous. How do we get the tangent? We take the limit. The tangent is a derivative. Whoa, 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 what did I just say? This is important. The tangent is the derivative. The tangent at a point is the derivative at a point. Let me say it one more time. The tangent of a point at a point is the derivative at that point. And that's that whole limit process that we did. So finding the derivative means finding the tangent line. Finding the tangent line means finding the derivative at a certain point. In terms of rate of change, it's the instantaneous rate of change right there. The derivative is the instantaneous rate of change, which is a tangent. The secant is an average. I'm going to write it out one more time. That's how important this is. I've said it several times, and I've kind of like been a broken record here, and you've probably tuned me out how many times I've said it, so I'll write it. The secant yields an average. The tangent is a derivative, which yields an instantaneous rate of change. All right. So that is how all of this is related. So now one more thing to make sure you're aware of. When we talk about velocity, the rate of change of the position of the function is equal to the velocity of the particle at time t. So the rate of change is that velocity at time t, f of a. When I talk about speed, that's the absolute value of the velocity. The speed would be the absolute value of that derivative. So again, the rate of change of a position function is equal to the velocity at time t equals f of a. So the speed is the absolute value of the velocity, which is the derivative of a. Speed, remember, velocity is directional. Velocity can go forward or backwards. When we're talking about speed, we don't care if it's going forward or backwards. We just want to know the quantity, how much, how fast. Now, if I take a rate of change, an average, over a distance, that's an average. Okay, so if I say delta S over delta T, and we'll talk more about this later, if I say delta S over delta T, this gives me an average, right? But if I want the derivative of S, the derivative of the position, that will give me the speed, or I should say the velocity. Let's erase that because it could be directional in this case. So that will give me the velocity at that particular point in time. So this is instantaneous velocity. Yeah, I spelled it wrong, but just deal with it. So this is instantaneous velocity when I take the derivative, whereas I take it over time like that, that's the average. All right, let's take a look at a couple examples here and begin with this. On this first one, it says, find the equation of the tangent line to the graph at the given point. So this was the PQ thing that we did, but we're going to do it now with our derivative formula. So over here, let me remind you what our derivative formula is. The limit as h approaches 0 of f of a plus h minus f of a all over h. Now we need to determine what these values here. Now for this particular problem, we need the slope at x equals 2, right? So that's what we're looking for. So this is our a value. So if I were to plug this into my equation here, I would have the limit as h goes to 0 of f of 2 plus h minus f of 2 all over h. Now looking at my equation, my f of x is equal to 9 minus x squared, right? I'm looking at it from right there. So now if I put in f of 2 plus h, I would get 9 minus 2 plus h squared, just like that. So that's what I'm going to substitute in here. So I will have the limit as h goes to 0. Now we said f of 2 plus h is this value. So this becomes 9 minus 2 plus h squared. Now I want to substitute the other value in. I want to substitute f of 2 in. F of 2, when I plug it in, I get 9 minus 4, which is 5. So this would be minus 5 all over h. Let me highlight again how I got these. 2 plus h, right here, that's what this came out to be. And then f of 2, that's what that came out to be. So I substituted those in from the equations that I got. All right, so now let's continue on with this problem. So the limit as h goes to 0, and I'm going to clean this up. This becomes 9 minus, let's go ahead and FOIL out the top. I'll get 4 4 plus 4h plus h squared minus 5 all over h. So what I did was FOIL that 2 plus h squared out. And so now at this point, I can clean this up again. I'll get the limit as h goes to 0. And when I clean all this up, I'm going to save you the little extra steps in between. I will get negative 4h plus, or minus, minus h squared all over h. So over here, I could say the limit as h goes to 0, and I'm going to take out an h. And I'll get negative 4 minus h all over h, right? And these reduce out. So I'll get the limit as h goes to 0, so this all equals the limit as h goes to 0 of negative 4 minus h. And so then when I plug in h now, I can find this limit and do direct substitution. I'm going to plug this in right here. And guess what? I'll get negative 4. And that is the slope. Okay? So that's how we've changed how we're doing the P goes to Q thing. So now let me just finish this and give you a final result. So y minus y1, which is 5, equals negative 4 x minus x1. So we put in our slope, our over here x1, y1 points, and we are all set. And this became my tangent line to this graph at that point. And that's how we solve for this. There is a shortcut. There is a shortcut, but we're not going to learn the shortcut just yet. So we're saving the shortcut. That's something special. We're going to get there eventually. This is how I want you to do these right now. Let's look at our next problem. All right, so let's slide this down. Right here, we have to find the limit. Over here, we have to find the equation of the tangent line, so it means we have to find the limit. I know my limit formula. I'm going to do this problem starting up here. Let's find, we have the limit as h approaches 0, right? And this is going to be a. So remember, it's f of a plus h minus f of a all over h, the limit as h goes to 0. So this will be f of 3 plus h minus f of 3 all over h. Finding what f of 3 plus h is. F of 3 plus h means I'm going to put that in there. So that's going to be a little funky. That's going to be the limit as h goes to 0 of 9 over 3 plus h squared minus f of 3 comes out to be 1 in this case. So minus 1 all over h. And so now we can continue on. And I'm going to FOIL out the bottom. So the limit as h goes to 0 of 9 over, this will be 9 plus 6h plus h squared minus 1 all over h. Okay, so now I'm going to find a common denominator. Here's a question you guys always say, Mr. Netzer, how do you get from this step to the next step? I'm finding a common denominator at the top. Okay, so I'm finding a common denominator at the top. And that common denominator is 9 plus 6h plus h squared. Mr. N, how'd you get that? This is 1 over 1, right? That's how I got that. I found a common denominator. On this side, it already had it, so it's 9. Now this will end up being on this side 9 plus 6h plus h squared. Okay, these are called complex fractions. So you need to remember how to do complex fractions. So that's the limit as h goes to 0. So now let's clean up the top. I'm going to save a couple steps because I'm running out of room. So you can distribute the negative, combine like terms, do all that good stuff. You'll end up with negative 6h minus the h squared all over the 9 plus 6h plus h squared all over the h. So over here I'm going to take this h out. So I'll have h and then negative 6 minus h all over this 9 plus 6h plus h squared all over h. Limit as h goes to 0. Those reduce. That was my goal right here. Okay, but now look what I end up with again. I end up now with the limit as h goes to 0 of this negative 6 minus h over 9 plus 6h squared, or sorry, 6h, okay, plus the h squared. So if you plug in 0 at this point and try direct substitution, plug it in right here. That goes to 0, that goes to 0, that goes to 0. So you'll end up with the limit equaling negative 6/9. So this equals negative 2/3. So y minus y1 in this case was 1 equals negative 2/3 x minus x1, which was 3. There's our tangent line. All right. Moving on. So you do these next problems the same exact way. So let's slide this up. And I don't have a lot of room here, but I will squeeze it in somehow. So let's take a look at this. And over here, notice, I don't have a value here. I don't have a point. I just have a. So the limit as h goes to 0 of f of a plus h minus f of a all over h, but I don't have a point. So guess what my point is? It's just a. So I'm going to put a in there. So f of a is 7a plus 3. F of a plus h will be 7a plus h plus 3. So those are the values I'm going to plug in there. So here's what I end up with. This becomes the limit as h goes to 0 of 7a plus h plus 3 minus 7a plus 3 all over h. Cleaning this up, I get the limit as h goes to 0 of 7a plus 7h plus 3 minus 7a minus 3 all over h, right? Those go away. These go away. I'm left with 7h over h as h goes to 0. Those reduce out. I'll end up with 7 as my slope. And here it's just telling me find f prime of a. It's not asking for an equation, just the derivative, the slope of the tangent at a. So it's very general. So now let's take a look at number 4. Okay, so it's the same situation. We have to do this as general as possible. So I'm going to we need to find f of a, obviously. So f of a will be 3a squared minus 2a plus 1. And then f of a plus h will be 3 times a plus h squared minus 2 times a plus h plus 1. Now, putting these two in our formula, this one right here, we have the limit as h goes to 0 of, now f of a plus h will be 3a plus h squared minus 2a plus h plus 1 minus f of a, which is this whole 3a squared minus 2a plus 1 all over h. And I'm going to continue this right up here because I need all this room. So the limit as h goes to 0. Now I'm going to FOIL this part out and combine some terms. And, well, let's just FOIL it out and start to clean up a little bit here. So this becomes 3 times it's going to be a squared plus 2ah plus h squared minus, and I'll combine these right here, 2a minus 2h plus 1 minus 3a squared plus 2a minus 1 all over h. So I went ahead and distributed that negative over there. So now this becomes the limit as h goes to 0, and this is going to be 3a squared plus 6ah plus 3h squared minus 2a. Well, we can do this right now. We can get rid of these, right? And then, so that's gone. And then we can get rid of those, so that's gone. So really what I just have left is minus the 2h minus the 3a squared. So all over h, these are going to reduce out. And then I'll just be left with this part right here, 6ah plus 3h squared minus 2h all over h. And what I'm going to do is I'm going to factor an h out of that. Because remember, you're always trying to reduce it with what's on the bottom. So this is the limit as h goes to 0. Because you want to get rid of that h because you have the limit as it goes to 0, right? So this leaves me with 6a plus 3h minus 2. Now, plugging in the limit as h goes to 0, that means I'm going to do direct substitution and plug that in there. So this leaves me with 6a minus 2 as my final answer. All right? So that's what f prime of a is. Okay, moving on. Again, just let me show you what I did. Right, I plugged in the 0, that reduced this out to 0, then I just had the 6a minus 2 left over. Okay, so over here, each limit represents the derivative of some function f at some number a. State such an f and a for that. Well, what we are looking for here is pretty much our original f of x. See how I did the a plus h things there? So I'm looking for my original f of x for this equation. So here, what I have to do is I have to try to take a look at this. And I have 4, it looks like minus, this is a plus h, right? That's what it looks like here. It looks like I've written an a plus h in there, which means my a is 1, and my f of a is 3, it looks like, right? Because this is f of a. Remember, I have f of a plus h minus f of a all over h. So it looks like I did 4 minus, here's your a plus h. So when I examine this, it looks like what I've got going on is 4 minus x squared. Now let's see, will that work? If a is 1 and I put in 1 here, 4 minus 1 squared, I will get 3, which is what I got right there. So it does work, and so f of a, we knew it was 3, and that does work, and it works in my equation. So this f of x originally was 4 minus x squared, right? And then when I did this, if I said f of a plus h, and I did f of a, in this case, a being 3, I'm sorry, yeah, a being 1, I would end up with that. So f of x equals 4 minus x squared, and this is at x equals 1. So let's clarify that. All right, let's do one more here. And I know there's a couple more examples, but I will do those in class. But let's just do this next one. This one we're going to need quite a bit of room for, so let's make sure we've got that room, and let's go through it. It says, at time t equals 0, a diver jumps from a platform diving board that is 32 feet above the water. The position of the diver is given by that equation. This is a position equation, and it even tells me that. Where s is in feet and t is in seconds. When does the diver hit the water? So, for part A, when the diver hits the water, we need s of t to be 0, right? That's the position, needs to be 0. So that means 0 equals negative 16t squared plus 16t plus 32. I can go through and solve for this, and what I'll do is I will factor it. I will take out, first we could take out this negative 16, and I'm left with t squared minus t minus 2. So I'm going to end up with t plus 1, t minus 2, and that's my 0. T is going to end up being 2, and negative 1, right? And negative 1, but we're going to throw that out because time cannot be negative. Not yet, at least. We haven't, we're getting there. We're starting to, get into the basics of time travel, apparently. But as of right now, time cannot be negative. So we are not going to do anything with negative times as far as we're concerned. So we're throwing that one out, and it's t equals 2 seconds. All right, let's look at part B now. What is the diver's velocity at impact? So I need the velocity at t equals 2 seconds, because that's when he impacts the water. So we need the velocity at 2 equals 2 seconds, and guess what? Guess what kind of velocity this is? This is an instantaneous velocity because I want it at a specific point in time. I'm not saying what is his average velocity when he jumped off the platform to when he hit the water. I'm not asking for that. I'm saying what is the velocity when he actually hit the water. So that is an instantaneous velocity. So since it's instantaneous velocity, we need this s prime of t. We need the derivative. The derivative is the tangent, which gives us the instantaneous, as I've said it so many times already in this video, at the beginning of the video. The derivative is the tangent line, and that's how we get the instantaneous velocity. And at what point do we need it? We need it at t equals 2 seconds. So let's go through and do that. How are we going to get the derivative? Well, we're going to use our derivative formula. The limit as h goes to 0 of f of a plus h minus f of a all over h. Again, there is a shortcut, but we are not using that shortcut yet. We are learning it this way. And I'll show you why as well when I go over a couple other problems, why we need to know it this way. Okay, so now what I need to do is I need to put this equation right here into that. So S of A, let's figure this out. S of A equals negative 16, A squared plus 16A plus 32. S of A plus H, this is negative 16 A plus H squared plus 16 A plus H plus 32. But I have something handy here. Guess what I know? I know A is 2, right? A is 2 because t equals 2. So I know A is 2. So here I can just clarify this and make this really easy, because if you do the A plus H, it's going to be a nightmare simplifying this thing. But since we already know what A value is, it's 2. That's where I want this to happen. I know that it's hitting the water at 2 seconds. So S of 2 ends up being over here 0. I'm going to have to do calculations. Why? Because I know when I put in 2 seconds, guess what? I've hit, this is S, I just did it in part A. But for this one, we're going to need S of 2 plus H. And if you don't believe me, you could put in 2 right here and right there and see that it'll come out to 0. All right, so this becomes negative 16, and this will be 2 plus H squared plus 16 times 2 plus H plus 32. Could you have done it with A and then substituted in 2 later? Absolutely, you could have. But I'm telling you, it's going to be really, really, really messy. So let's put this in our formula. So over here, because remember, we had 2 plus H, 2 plus F. So the limit as H goes to 0 of this thing now, it's going to be negative 16, 2 plus H squared plus 16, 2 plus H plus 32 minus F of A, which we said was 0. In this case, it's S of A all over H. All right, so over here, the limit as H goes to 0, and this becomes negative 16, and this will be 4 plus 4H plus h squared plus, I can distribute this. This will be 32 plus 16h plus 32, just like that, all over h. And then I could distribute this 16, the limit as h goes to 0. And this will be, when I distribute, I'll get negative 16 times 4, so that'll be negative 64. And then it'll be minus 64h minus 16h squared plus, I can combine these, 64 plus 16h all over h. So what you'll notice is you should always have things that reduce out here. All right, so over here I have this 64 and that 64 that reduce out. And that's pretty much what all I get to reduce, but then I can combine this and this to give me the limit as h goes to 0 of negative 48h minus 16h squared all over h. But then I could take this h out, right? And I'll have negative 48 minus 16h all over h, and that reduces. So then I end up with the limit as h goes to 0 of this negative 48 minus 16h. Do direct substitution, plug this in, that goes away, and my answer is negative 48 feet per second. And that is the velocity when the diver hits the water. So it's the instantaneous velocity at t equals 2 seconds. All right, so I will save the rest that we have. We're going to do a couple more examples in class, and I'll explain to you why you need to know this long version of the derivative. All right, so thanks for watching. Hit that like and subscribe button, and I will see you guys in the next video.